All right, so let's move on to acceleration. Before we do that, though, I just want to go over one quick review question just to make sure you do have uniform motion down. So we got a cat running at a velocity of 9 meters per second west. Okay, if you need to draw, always draw this at the kind of top of your page, just so you always have it, right? So we know that's north, south, east, and west. Okay, so of course west is to the left. All right, and if it runs at the same rate for 7.2 seconds, what is its displacement? So we have velocity, time, and displacement. So it looks like we are working with this equation, V equals D over T, which of course is what we always use when we have nice uniform motion. And that means something moving at a constant rate. Okay, but we have here velocity, and we have time, but we don't have displacement, right? Here's my velocity right here. Here's my time, but I need displacement. So therefore, I need to rearrange this equation to figure out what displacement is. So how am I going to do that? Well, if we take a look here, right now we are dividing that d by t. We need to do the opposite to get it all by itself. What is the opposite of dividing? It is multiplying. So I'm going to multiply that side by t. Anything you do to one side, you got to do the other. Those guys cancel out, which is exactly what we need. And look what we got. We got TV. But more importantly, of course, we have an equation for displacement, which is what we need, right? So displacement is just equal to the time times the velocity. And so that's what we're going to do now. So we got 7.2 seconds. Okay. And then we need the velocity. Now remember, 9.0 meters per second west. Since it's going west, that means it's going to be a negative 9.0 meters per second. Okay, so really important that you know that, because that's going to help you get the direction of your displacement. And so what do we get? What's 7.2 times 9? So that there gets us negative 64.8 meters. Now, remember, there's a few other things that we need to keep in mind. So in answers in physics, we also always have to keep in mind three things: units, significant digits, and direction. Okay? So first of all, significant digits. Let's go over that. Well, 9.0 has 2 significant digits. 7.2 has 2 significant digits. So our answer, since we were multiplying, should also have 2 significant digits. So first off, the 64.8 should just round up to a 65. I'm going to keep that negative there. Of course, we already had the units. That's good. And so finally, we just need direction. Well, since it's negative, that means it's going west. Okay? And that makes sense, right? If you're moving west, then your displacement's obviously going to be west. Okay? And direction is just going to become even more important today when we review or go over acceleration. When I say acceleration, what comes up for you? Hopefully some of you said or thought speeding up. It also means slowing down as well. So acceleration is just a change in velocity. Any sort of change in velocity means it gets bigger, it gets faster, or it gets slower. And that's what acceleration could be, okay? So any sort of change in velocity over a specific time interval is acceleration. Really important to note, this is not uniform motion. Oh my goodness, so important right there, okay? Why is that so important? The reason it's so important is because we have an equation that we can use specifically for uniform motion. We just used it right here. So when we don't have uniform motion, then we can't use that equation. So can't use V is equal to D over T because that's for constant velocity. That's for uniform motion. When you don't have a constant velocity, you can't use this equation, okay? So that's really, really important to note that this is not uniform motion, because uniform motion is when something's moving at the same speed for the same amount of time and not changing direction and all that fun stuff, okay? Acceleration is a vector, so direction does matter. And therefore it can be positive or negative. Now, most people see positive and negative and they just think, oh, well, that means positive must be speeding up and negative must be slowing down. Absolutely not, because we know that positives and negatives tell us what direction it's going. Has nothing to do with speeding up or slowing down, okay? So here is our equation for acceleration. So acceleration is equal to delta. What's that delta again? That's this thingy. That means change in. Okay, so change in velocity over change in time. So, of course, if we want the change in velocity, we go to final velocity minus initial velocity. Okay, so that's so important that you remember that delta V is equal to final minus initial. Always, always, always. Now, sometimes we do a final time minus initial time, but often we don't. So that's kind of a funny way of putting it that I don't love. Okay, so often they just give you how much time it happened over, and that's all we need is like, we just need how much time did whatever take to accelerate. And that's just the time that we need to divide by. Okay, so very rarely are we going to be using final time and initial time. It's usually just going to say, oh, this happened over 30 seconds or something like that. Okay, but that is our equation that we're going to use. Final velocity minus initial velocity over time, and that is acceleration. Okay, so and remember, it is a vector, so we need to keep these little arrows on top of everything. Okay, so another thing you want to know is that the units for acceleration are meters per second squared. We have that little 2 above the seconds. That just means the seconds are squared. So something really important to note, velocity has units meters per second. Acceleration has units meters per second squared. Please do not confuse the two, okay? If you see meters per second, you have been given velocity. If you see meters per second squared, you have been given acceleration, okay? Please do not mix those up. I know they look similar, but they are very different. Okay, so how do we know something is speeding up or slowing down? That's my question, because a lot of people just think, oh, well, negative acceleration must mean it's slowing down. That's not it at all. So I want to think about this. What if we have positive acceleration versus negative acceleration? So let's go over this first situation here. Okay, so say we have both, we're moving in a positive direction, and then the change in the magnitude of our velocity is also in a positive direction. Okay, so this is really just telling us the velocity, and this is telling us the acceleration. So positive direction, let's just choose east or right, because yeah, it's just most often the one that we use. So if we're moving this direction, and then you have acceleration, oopsie, that also moves you in that direction, what happens? Oh, that becomes even bigger, right? Because you have two things going in the same direction. So this guy is speeding up. Okay, now, what if the opposite happens? What if the acceleration is still positive, so therefore to the right, but its initial direction is 0? So that's this next one we're going to go over. So the initial direction is negative. So our initial velocity is negative, so that would be to the left, right? And then what if the acceleration, though, was this way? What happened? Is the acceleration helping that speed up, or is it working against it and slowing it down? It's definitely working against it and slowing down, because look what happens to the resulting vector here. It's not as big, right? So therefore, this guy is slowing down. Okay. So that's positive acceleration, but guess what? It's slowing down. So again, just because it has positive acceleration does not mean that that it's getting faster. Okay, let's go over instance 3 here. So we have a positive direction initially, but the change in magnitude, the acceleration is going to be in a negative direction. So say something's going to the right to begin with. Okay, so that's its initial velocity. And then the acceleration is going in a negative direction. So in this case, that would be to the left. So there's my acceleration. What just happened? Oh, again, we have the acceleration working against the velocity, and we don't have as big of a vector arrow anymore. So therefore, this is also slowing down. Are you noticing a pattern here for when it's slowing down? So let's go over our fourth and final instance on the left corner here. So here we have our initial direction, velocity in a negative direction, and the change in magnitude in a negative direction. Okay, so for example, say velocity is going to the left, and then our acceleration, guess what, is also pushing it to the left. What happens there? We're going way more to the left. So this is speeding up. Do you notice the difference? Do you notice what will determine whether it's slowing down or speeding up? So what will determine is if it's speeding up, then the velocity and acceleration will be in the same direction. If it's slowing down, they're going to be in opposite directions. So that is the most important thing to know about acceleration and its directions. Okay? So when velocity and acceleration are in the same direction, then we're speeding up. So that's what's happening on this side. However, when velocity and acceleration are in opposite directions, we're slowing down. Okay? So that's what you have to know about acceleration and its direction with regard to its velocity. Okay, so another way to say it, if you have positive acceleration, that is going to occur when you have an object's velocity that's increasing in a positive direction or decreasing in a negative direction, right? Increasing, positive, because we have positive acceleration, same sign. Decreasing in a negative direction, negative and positive, therefore opposite sign, so of course it's decreasing. You're going to have negative acceleration when the velocity is decreasing in a positive direction. Okay, so the velocity is still going to the right, but of course, since it's slowing down, it's going to be negative acceleration. Or if something's increasing in a negative direction, so it's going left and then it's speeding up left, then we have a negative acceleration. Another example of this is, well, why don't I just show you? All right, so here's an example of how we want to think about acceleration when it's slowing down and speeding up, but that in relation to its directions. So I'm going to throw a ball up. It's actually not a ball, it's actually like a lip chap. Oh, it smells so good too. It's nice and brand new. Oh, anyways, it's closest thing to that I have to a ball in my house. Yes, I am that athletically challenged. I do not have any sort of ball in my house. So I'm going to throw this ball up and down. So as it's going up, I want you to focus what's going on as I throw it up. Is it speeding up or slowing down as I throw it up? Oh, I'm throwing it too high, you can't even see it. Speeding up or slowing down as it just goes up. I'm going to slow-mo it now so you can see, is it speeding up or slowing down as it goes up? slowing down as it goes up, right? Obviously not as it goes down. So it's slowing down as it goes up, but that's up is a positive direction, right? So its velocity is still in a positive direction, but what's its acceleration? Downwards. Because guess what? Guess what's working downwards? Gravity. It's that, this thing that's pulling us all towards the earth. So since its acceleration is downwards, but its velocity, the way it's going, is upwards, guess what's happening? It's slowing down. And then let's focus on what happens when it comes back down. Let's try that again. There we go. Is it speeding up or slowing it down as it goes back down? It's speeding up because its velocity is downwards, right, which is negative, and its acceleration is also negative. It's downwards because, of course, that's what gravity does. It pulls us down towards the earth, right? So that's an example of how having velocity and acceleration in the opposite direction will slow something down, and having them in the same direction will speed it up. So again, a lot of people think that negative acceleration automatically means you're slowing down. It doesn't. So that's an example where negative acceleration actually means that you're speeding up when it's going down. Okay, so hopefully that helped you. Hopefully made some sense to, again, help you just with these directions of acceleration, because it is just so important. Okay, now we're just going to go over a bunch of examples, because that's just the way to do this and to figure this out. It's just to do a ton of examples. Okay, so let's just do one really easy one to begin with. Car accelerates from rest. Okay, so here's the thing about word problems, because I'm sorry to tell you, physics is just word problems. It's just all it is. So as soon as you come to a piece of information, write it down, okay? So my first piece of information you probably didn't even see, but accelerates from rest. What does that mean? It means from rest. It means what's your initial velocity? Your initial velocity is 0 because it starts at rest, meaning it starts not moving. So anytime you see it starts from rest, you know, oh, initial velocity is 0. Okay, what's next? It accelerates to 30 meters per second. Another piece of information, that's probably our final velocity. So that is 30 meters per second, and that's north, which is a positive direction, so I'm just going to keep it positive there. Okay, and that happens in 5.2 seconds. What did they give us there? They gave us the time it took. Okay, so that's what I want you to do for every single question here in physics, is always write this stuff down. Write down what you have. Okay, please, please, please. Okay, so what is our equation for acceleration? Do you guys remember? It was final velocity minus initial velocity divided by time. Okay, that's kind of the format that I want you to think of most often. Great, we have final velocity, we have initial velocity, we have time. So let's just plug in all these numbers. Our final velocity was 30 meters per second. Okay, it's north, so I'm going to keep that positive. And then our initial was 0, so we're going to subtract 0. And then we're going to divide that by how much time it took, which is 5.2 seconds. Okay, so what do we need to do? We need to do the subtraction first, which in this case is super duper easy, right? 30 minus 0 is just 30. And then we can do dividing by the 5.2. So you're going to want to work out that whole numerator first, okay? And when we do 30 divided by 5.2, we get 5.769, so on and so forth. And our units there are meters per second squared. Okay, so again, remember, 3 things we need when we answer physics questions. We need to know the correct number of significant digits. Here we have 2 with 30 and 2 with a 5.2. So we should probably have 2 here. So 5 point, and then we'll end it at the 7 here, but we need to round it up to an 8 since there's a 6 next to it. Units, meters per second squared. and direction. Okay, well, here's a little tip. As long as you put your negatives and positives in correctly in the formula, the answer is going to give you the direction. If it's negative, then it's in the negative direction. If it's positive, it's in the positive direction. Here, since the positive direction was north, and then the negative direction is south. Also, think about it. It's accelerating from rest 230 meters per second north. Its acceleration is probably also north, right? Because it's pushing it north. Okay, so there is our direction. So there we go. That's it for that question. So that's really just kind of showing you how to plug in the numbers into that formula, and also that from rest thing. That is so important that you know about that. Okay, let's do another one. We have a car traveling 70 kilometers east. Oh, so again, as soon as you see a piece of information, I just want you to write it down. Okay, that looks like our initial velocity, so 70 kilometers per hour. Okay, east, so make sure you put that direction on there. Good. Changes its velocity to 90 kilometers per hour east. Oh, well, that looks like that's its final velocity. Great. Of course, east as well, so it's speeding up. And that happens in 4.5 seconds. So there we go, there's our time. Okay, so we need to determine the average acceleration of the car in meters per second squared. Oh boy, okay. We need it in meters per second squared, and we are given velocity in kilometers per hour. That's a problem, okay? So anytime you see that, if you want meters per second squared, I need my velocities in meters per second. I cannot have them in kilometers per hour. So we are going to have to take these kilometers per hour, and we're going to have to take or convert them to meters per second. So a reminder of how to do that, because again, it's so important. I'm using this factor label method where I get rid of what I don't want to get what I need. Okay, kilometers here. I need meters instead of kilometers. So I need the kilometers to cancel out. So I'll put kilometers on the bottom so they cancel. And meters on the top because I need meters on the top. And then again, what's the relationship we know? Oh, we know for every 1 kilometer we have 1,000 meters. So that's what I'm going to do there. Let's take care of the hours and seconds thing there. Okay, hours on the bottom here, so they need to be on the top. And I want seconds on the bottom. Perfect. So we leave that there. What's the relationship? For every 1 hour we have 3,600 seconds. Okay, so what does that mean? That just means you're taking 70, multiplying it by 1,000, and then dividing it by 3,600. Okay, so if we do that, we get 19.4 continuing meters per second. I'm going to leave that continuing there for now, just because when I do my calculations, I want as accurate values as possible. So let's do the same thing with 90. I'm just going to do it really quick. Okay, so there we go. We get 25 meters per second when we do that. Okay, so now we have our initial and final velocity in meters per second, our time in seconds, so we can go back to our acceleration formula and figure out how this works, okay? So again, we know final velocity minus initial velocity divided by time. Okay, so my final velocity was 25 meters per second. Then going to subtract my initial velocity, which was 19.4 continuing meters per second. So in my calculator, I'll just put like 19.44444444 just to get a more accurate answer. And then I'm going to divide that by 4.5 seconds. Okay, so first 25 minus 19.4444444444. That is 5.5 continuing meters per second. And then we're going to divide that by 4.5 seconds. What do we get? We get 1.23456. Oh, cool. We get 1.23456, 7. Isn't that cool? How often does that happen? Meters per second squared. But I got a spoiler fun because, of course, we need the correct number of significant digits. So I'll put that down here. So, of course, what do we need? We have 2 here, 2 here, and 2 here. So we just need 2. So that's going to be 1.2 meters per second squared. And then we need the direction. So it was going east. It got faster east. So therefore, the acceleration must also be east because it made it speed up to the east. Okay? And there we go. Next one. Yeah, I told you we're doing a bunch of questions. We have 2 more, okay? So hang in there. You can do it. Car traveling at 25 meters per second east accelerates at 0.50 meters per second squared. Okay. Oh, sorry. I just went through a bunch. So first, it's traveling at 25 meters per second. Okay, so that looks like initial velocity to me. I don't know about you guys. Okay. And then accelerates at, oh, it gives us acceleration this time. That's not something we usually get. So 0.50 meters per second squared. Great. So if it takes 5 seconds to pass the vehicle, oh, wait, just gave us another thing, gave us time, write it down, then determine the final velocity. So we're looking for this final velocity. That's what we want to know. Determine the final velocity traveled by the vehicle. Okay, so this is going to be one of those tricky situations where we have to rearrange, okay? And this is not going to be an easier one for you guys to rearrange. It's going to be one of the more difficult ones. So, if you ever have a hard time rearranging while there's still all the letters there, something you can do first is actually plug in the numbers you have. So I'm going to do that. I have to put in the units because it just feels so wrong to me not to do that. But some of you, just to help you with rearranging, might want to leave out the units for a second. But anyways, that might help you a little bit more, and that is completely fine because then you're just like, okay, trying to isolate EF, and I have all these other numbers here now instead of letters. Okay, what do we have to do first? Now, usually, so with VF here, we are subtracting 25, dividing by 5. Usually you deal with the addition and subtraction first when you're solving equations, except for in this situation, because I am dividing not just the VF by 5, but also the 25. Okay, so I actually have to take care of that first. Because if we just add 25 to both sides, that's not accounting for the fact that we are dividing 25 by 5. So I'm going to get rid of that first. So that means I have to multiply both sides by 5 seconds. Okay. So, oh, I just put 0.5. That's just supposed to be 5.0 seconds. Oopsie. So 0.5 times 5 then is 2.5. If you don't know the units there, that's okay. It is meters per second. And then we are left with VF minus 25 meters per second. Okay, now what do we do? Well, we can just add the 25 to both sides. If I add it here, gets rid of it. That's negative 25 plus 25 is 0. And then I'm going to add it here. Okay, and then what do we get at the end of the day? 25 plus 2.5. That is 27.5 meters per second. And there's your final velocity. You got it. Okay, but of course we need the 3 things. We need significant digits. So first of all, there's 2 there. 2 there, remember that 0 does not count. And there's 2 there, so looks like we need 2, not 3. So this will have to round to 28. We need our units, meters per second. And we need our direction, which again, here we have something traveling east, then accelerating while passing the other vehicle. So it's speeding up, right? So therefore, this is also going to have to be east because it's speeding up to the east. So obviously, there you go. So it's east. All right, we got it. That's our final answer. Okay, just a note here. Again, these are difficult times, so I'm going to give you guys a little treat, and you can write these on your formula sheet. I'm allowing you to. here is a rearranged version for final velocity if you need to rearrange this equation. Okay, here's a rearranged version for initial velocity if you ever need to find that. Again, I am allowing you to write this on your formula sheet for now. And for time. So if you ever have a situation where you have final and initial velocity and acceleration, you need to figure out how much time it took, then you can use that. So those are all your rearranged equations for this acceleration formula. Okay, one more question. Let's do it. So we have a baseball entering a catcher's glove at 12 meters per second east. So there we go, there's our initial velocity. 12 meters per second east. So since it's east, I'm going to keep it positive. Comes to rest in 0.65 seconds. There's our time. Wait, it just gave us something else really, really sneakily. What did it give us? Comes to what? Oh my goodness, rest. What does that mean? That means our, in this case, final velocity is 0. Which makes a lot of sense because, you know, if the catcher is catching a baseball, then obviously the baseball comes to rest, meaning it stops moving. So there we go. And we want the acceleration of the ball here. Okay? So back to just plugging in numbers to formulas. Yay! With acceleration equals final velocity minus initial velocity divided by time. Okay, so here, what was our final velocity? It was 0 meters per second. What was our initial velocity? It was 12 meters per second. What was the time it took? 0.65 seconds. Okay, so again, numerator first. 0 minus 12 is negative 12. Ooh, wonder why that negative's there. Interesting. I wonder if that tells us something. It obviously does. But let's divide 12 by 0.65 first. And if we do negative 12 divided by 0.65, we get negative 18. I'm just going to go right to significant digits now. I can see that it's 2 again. So, yeah. So negative 18. And then, of course, it's acceleration. So what is our units? Meters per second squared. Here's the question though, direction. So as I said before, if you put in the correct if you put in the correct signs like positives or negatives into this acceleration formula, it will usually give you what direction it's going in as part of the answer. Here it gave us a negative answer. So what does that mean for the direction of the baseball? Of the acceleration of the baseball. It means it's going west, not east, right? Because it's negative. So, and if you think about that, the baseball's slowing down. So if we know it's slowing down, its initial velocity was east or to the right, and it's slowing down, therefore its acceleration has to be opposite to that. So it obviously has to be to the west. Okay, and so there you go. There's an example where we have those opposite velocities versus accelerations, and of course means that something's slowing down. Okay, so you guys practice with these equations, with these kind of questions, okay? Make sure you write down all these rearranged equations for you. So those are, other than, A is equal to VF minus VI over T, those are all the other possible equations you would need to solve for final velocity, initial velocity, or time. And otherwise, just practice a bunch, okay? Because this is definitely one of the more difficult parts of the physics unit. So be prepared for that, but also how you get through it is just by doing lots of practice questions. Okay, you guys, I believe in you. I know you can do it. Good luck. Please, 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 please make sure if you have any questions, ask. I'm happy to answer any questions. You can comment on this video. You can email me, okay? And yeah, good luck.